Hello everyone, my name is Nikita, and in this talk I will introduce Slingshot, a system that enables fault tolerance and live upgrades in virtualized radio access networks. This work was done at Microsoft Azure for Operators in collaboration with LG from UT Austin and our colleagues from MIT and Cornell University. As most of you know, cellular networks is the infrastructure which allows our phones to connect to the internet over the air. The heart of every cellular network is called radio access network, or RAN, which converts wireless signal samples received from base stations into the packets via signal processing. Traditionally, RAN is implemented using specialized DSP hardware or FPGAs. Virtualized radio access networks, or VRAN, is a new concept where RAN processing is moved to software running in a general-purpose data center connected to the cell sites over Ethernet. VRAN offers reduced vendor lock-in, rapid development and upgrade of system components, easier maintenance, and potentially lower cost of ownership. The VRAN market is growing across the world, with, for example, Rakuten already deploying 30,000 units in Japan. Now, let's take a look inside a typical edge data center deploying VRAN. The data center contains a set of servers running the VRAN software. The servers are interconnected with a switch, which is also used to connect the data center to the cell sites over the front-haul Ethernet interfaces. One of the biggest issues with today's VRAN architectures is that their deployments miss resilience, an ability of the system to tolerate faults and undergo software updates with zero downtime. If a server running an instance of VRAN crashes, it will cause all connected cell sites to shut down. The figure on the right demonstrates the behavior of a video conferencing application running over a 5G phone connected to the internet over today's VRAN in the event of failures. The y-axis shows the achieved average video bitrate, and the x-axis shows the time. If a VRAN server crashes with either a software or hardware issue, the video call stops for almost 7 seconds. This is the time required for the phones to reconnect to another cells and restore the broken connection state. Such a long downtime is undesired in cellular networks and is critical for many applications which are envisioned to be using VRAN. Another scenario for resilience is software updates, which now require shutting down a set of cell sites, therefore reducing the overall coverage for the time of the upgrade. This animation shows the logical view of resilient VRAN operation when deployed with Slingshot. At the high level, Slingshot addresses aforementioned resilience concerns by allowing VRAN to transparently migrate processing between servers in a data center when handling failures or software upgrades. This way, cell sites never go down during resilience events, therefore completely avoiding service interruption. With Slingshot, our video conference never experiences downtime, and the bitrate remains stable through instantaneous failover. Now, let's see how Slingshot works. The edge data center runs the latency-critical layers of the VRAN stack, including the layer 1, or physical layer, also called PHY, and the layer 2, which includes the media access control layer. In this work, we focus on providing resilience to the most performance-critical part of VRAN, the baseband processing layer 1. This is a key component in VRAN, which runs the actual signal processing, such as Fourier transforms, error correction, and so on, over wireless samples to convert them into the user bits and vice versa. It might seem like VRAN, and particularly PHY, is not different from any other cloud application, and its resilience can be handled by existing technologies. Unfortunately, this is not true. The main challenge here is that PHY is a real-time software, which needs to do signal processing under a strict sub-millisecond time budget. If this deadline is violated, the VRAN will lose data or even crash. At first, we implemented PHY resilience via processing migration with KVM. As we found, PHY via migration takes at least 100 milliseconds, which is much longer than the required real-time budget. Another challenge is that all existing VRAN infrastructures are quite complex, often closed source, and designed to operate under certain protocols. So the resilience system must be completely transparent and interoperable with them. This, for example, precludes techniques such as putting all the state of the network function in an external reliable database. Now, we will discuss how Slingshot handles these challenges. The first challenge is how to move baseband processing between servers in real time. Our main insight here is to view wireless signal processing as a stateless functional execution. Let me show this with an example. Suppose the PHY receives a bunch of signal samples to process at the time window T1. During the processing, it generates an intermediate state, shown with red circles. Then, it receives the next batch of samples for the window T2, which will produce its own state. Our main observation is that there is almost no dependency between the states in two consecutive windows. This means that the window T2 can be moved to another instance of Phi running on a different machine without dealing with any state inconsistency. Now, what I mean by almost is that in real baseband processing systems, there is a little bit of state carried between the windows. One example of this is the cumulative average of signal-to-noise ratio, which is computed across multiple time windows. Here, we rely on another interesting observation, that such small state inconsistency does not introduce more errors than regular wireless impairments, which all cellular networks are designed to handle. In this example, the inconsistency might cause the value of SNR to quickly change. However, a natural sudden spike in signal quality will incur a similar impairment. This means that discarding this state does not impact the performance of the network beyond regular impairments, and we demonstrate this with end-to-end experiments and micro benchmarks. So the conclusion is that complex baseband processing migration can be reduced to simple rerouting of incoming and outgoing connections of the Phi. However, implementing such rerouting is still not trivial. As mentioned earlier, in today's VRAN, the servers are statically provisioned and interconnected with the cell sites and upper layers in a fixed way. This fundamentally disallows any flexibility in the system and only supports a fixed one-on-one mapping of layers one to another. To solve this, Slingshot introduces two new middle boxes. First, we disaggregate L1 and L2 layers and allow them to run on separate servers. This is done in the software middle box placed on the servers with VRAN. This middle box is also responsible for transparent rerouting of connections between the layers. The second middle box is based on a programmable switch and is dedicated to rerouting front-haul connections between the cell sites and the Phis in the data center. This middle box also runs the fault detection program entirely in the data plane. This helps Slingshot to enable fast and transparent fault detection with immediate failure notification. With such an architecture, Slingshot works out of box in already existing VRAN infrastructures, and its deployment does not require changes in any software or protocol specifications. This is the complete picture of resilient Phi operation with Slingshot. Currently, the bottom server is executing baseband processing for the MAC running in the middle. When it crashes, the P4 middle box detects the fault immediately and, in combination with the software middle boxes, reroutes all the traffic to the upper backup server, therefore tolerating the failure. Please see our paper for the internal details on those middle boxes. We evaluate Slingshot on an end-to-end wireless 5G testbed. The hardware part of our testbed consists of x86 servers equipped with 100 Gbps NICs and a Tofino-based programmable switch. The server is connected to a Foxconn radio unit. As the VRAN software, we use Intel FlexRAN and Capgemini Altran, and we deploy a commercial 5G Fusion core from Metaswitch. For evaluation, we use 3 different user devices, such as phones and Raspberry Pi boards. We first show that Slingshot sustains throughput during resiliency events. In this experiment, we send uplink traffic between the local server and the 5G phone over our VRAN. The graph at the bottom shows the uplink throughput over time, both for the TCP and UDP traffic. The y-axis shows the achieved throughput, and the x-axis the time. We crash the active baseband processing server at a random time and record the throughput failover. For UDP traffic, the failover with Slingshot happens immediately without any network downtime. The TCP connection, however, sometimes experiences a short downtime, which is related to the way TCP handles retransmissions. Note that TCP downtime is no more than 100 milliseconds in the worst case, which is much shorter than 7 seconds of blackout without Slingshot, as shown at the beginning of the talk. Next, we demonstrate how Slingshot enables live migration of the Phi with zero downtime. Here, we migrate baseband processing between 2 versions of Phi running different Phi configurations. The figure shows the throughput achieved by each device over the duration of the experiment. At first, a suboptimal Phi configuration causes unfair bandwidth distribution between the devices. For instance, the Raspberry Pi device shown with the green line gets a much higher bandwidth allocation than the phones. We then apply a planned update and move baseband processing to another configuration with a better bandwidth balancing. The important thing to note here is that with Slingshot, this upgrade happens instantaneously, with zero downtime of the cell sites and user devices. Okay, to conclude, I would like to say again that today's VRAN means resilience, an important feature of every cloud application. Our work is taking the first step in bringing resilience features such as fault tolerance and zero downtime maintenance into VRAN's baseband processing. Slingshot is based on our observation that inconsistencies in the Phi state are similar to regular wireless impairments, which VRAN can handle. This reduces complex state migration to fast but careful rerouting of protocol messages. Finally, we show how Slingshot coexists with existing VRAN infrastructures completely transparently through our new Middleboxes. We evaluate Slingshot on a real production-grade end-to-end 5G deployment, therefore demonstrating that our principles work in practice.